Welcome to this video on length contraction, part of our relativity series. Length contraction is one of the most fascinating predictions of Einstein's theory of special relativity. In this video, we'll explore how moving objects actually shorten along their direction of motion, and why this happens at speeds approaching the speed of light. So what exactly is length contraction? When objects move at very high speeds, they appear shorter along their direction of motion when observed from a stationary frame. It's important to understand that the object's length in its own rest frame, called the proper length, remains completely unchanged. Only observers who are in relative motion to the object will measure a contracted length. This isn't just an optical illusion or a trick of light. Length contraction is a real physical effect that was predicted by Albert Einstein's special relativity, and it fundamentally changes how we understand space and motion. The mathematical relationship describing length contraction is given by the Lorentz contraction formula. The equation is L equals L sub 0 times the square root of the quantity 1 minus v squared divided by c squared. This formula is closely related to the Lorentz factor, represented by the Greek letter gamma, which equals 1 divided by the square root of 1 minus v squared over c squared. This elegant equation tells us exactly how much an object's length contracts based on its velocity. Let's break down what each variable in the formula means. Capital L represents the contracted length, which is what an observer measures. L sub 0 is the proper length, which is the length of the object in its own rest frame. The letter V stands for the relative velocity between the two reference frames, and c is the speed of light, which is approximately 3 times 10 to the 8th meters per second. Understanding these variables is crucial for applying the formula correctly. Length contraction has several important properties that help us understand how it works. First, the contraction occurs only along the direction of motion. Dimensions perpendicular to the motion remain unchanged. Second, the effect becomes significant only at relativistic speeds, meaning speeds that are a substantial fraction of the speed of light. At everyday speeds, the contraction is so small that it's completely unnoticeable. Finally, the contracted length is always smaller than the proper length. In other words, L is always less than L sub 0. Let's work through a concrete example to see how this formula applies. Imagine a spaceship that has a proper length of 100 meters. How long does it appear to an observer on Earth when it's traveling at 0.8 times the speed of light? We're given that L sub 0 equals 100 meters, v equals 0.8 c, and we need to find L. To solve this problem, we start by applying the formula. L equals L sub 0 times the square root of 1 minus v squared over c squared. Next, we substitute our values. L equals 100 times the square root of the quantity 1 minus 0.64, which simplifies to 100 times the square root of 0.36. Calculating this out, we get L equals 100 times 0.6, which equals 60 meters. So the spaceship, which is 100 meters long in its own reference frame, appears to be only 60 meters long to an observer on Earth. That's a 40% reduction in length. Let's recap the key takeaways from this video. Length contraction is a real relativistic effect, not an optical illusion. It's a fundamental consequence of how space and time work at high speeds. Objects shorten only along their direction of motion, while dimensions perpendicular to the motion stay the same. The effect is also reciprocal, meaning each observer measures the other as contracted. This symmetry is a beautiful feature of special relativity. Length contraction reveals the profound connection between space and motion in our universe, challenging our everyday intuitions about how the physical world works.
If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.